today's lecture, I would like to say a few words about math aspirants. So I'm very happy to have been invited to deliver this lecture on Maths Aspirant platform. So Maths Aspirant is a valuable initiative started by Professor Vinod with the aim of helping students prepare for competitive examinations and develop a deeper understanding of mathematics. So in today's lecture, I will discuss some selected problems from CSIR net examination along with the solving questions. I will also try to explain thought process, important observations, and techniques that can help you to solve such problems more effectively in the examination. Okay, so I hope this session will be helpful for everyone and enjoyable for all of you. So I will not only tell you the solution of the questions, I also will let you know that how to get an idea to get the solution and how you solve some difficult part C problems in the CSI net exam. Okay, so and this the techniques and the way of the solutions and the way of thinking I will be letting you know in this lecture will be really helpful for you in the upcoming examination, which will be held on 17 July. Okay, so let's start. So I have picked the problems from December 2023, I think. So yes, and CSIR net July 2025. Okay, so not all are the very good problems, not easy ones. So sometimes student might skip these problems in the exam, but one can solve this. Okay, so in exam itself. So let's start with this problem of real answers. So this one. Okay, so I would, before each of the problem, I would like to give you some time to think. And if you know the answer, then you will raise the hand. I would like to know that how many of you can solve this problem. So please raise your hand if you can solve this. Okay, if you have already solved it and know the solution, you can raise your hand. So I might ask you. Okay, so what problem says? It says that let f R2R be a continuous function such that mod fx minus mod fy is greater than equal to log 1 plus mod x minus y for all xy in R. Which of the following statements are true? Okay, so first one says f is necessarily 1, f need not be 1. Okay, let's try to see that. So for a function to be 1, whenever fx is equal to fy, we should have x is equal to y. Okay, so it can be directly done via this inequality C. So assume that fx equal to fy. Okay, then we get
I think you didn't share the screen.
no, I have shared the screen, so I hope all of you can see it now, right? So please confirm.
Yes, sir.
There might be a problem from your side, so you can rejoin. Okay. Yeah. Okay. So we get this from the given inequality that this should be less than equal to 0 log 1 plus mod x minus y. Okay. So and we know that this is greater than equal to. Can you tell me? 0, right? This is greater than equal to 0 because log 1 0 and log 1 is a strictly increasing function. So 1 plus something, it might be 1, so it can be 0. And if it is this quantity is greater than 1, so it must be greater than equal to 0. So then what can we say? This must be equal to 0, right? If it is 0, then this value must be 0 because log is a 1 function. Everyone knows that. So this means that I mean to say this thing should be 0, right? So that this whole quantity is equal to 1. Okay. So this implies, and this can only happen if x is equal to y, right? So it means the function is 1. Okay, so the first one is wrong and the second one is correct, true. and f is necessarily onto and f need not be onto. So see, so if we want to know about the answer of 3 and 4, right, you can discard by picking an example, but if it is onto function, then you have to prove it, right? So how can you go? Okay, so see, whenever you have given a continuous function, if it is onto, then it takes every value, right? So limit x tending to infinity and extending to minus infinity, what should be that? It might be oscillating a minus infinity to infinity, or it should be minus infinity infinity, something like that, right? So there are two ways to prove it. This function is one onto. Okay, so one way is to show that the image is closed as well as uh, open of this function. Okay, so there are only two subsets of R which are open and closed. One is phi and another is R. Obviously, function is one, so the no function has empty image, right? So the image must be R. So that in that way you will try. Okay, so try to show that it is closed. Every Cauchy sequence converts there. Okay, so and openness is very easy. So let's see by other way. See, mod of fx. First of all, this is a continuous one function, right? Note that this is a continuous one function. Note that f is continuous and 1 continuous and 1 so f is strict monotone. So limits must exist, right? I mean to say they might exist infinitely, but exists, right? So it might be possible that limit extending to infinity is infinity, limit extending to minus infinity is minus infinity, but it will not be oscillating because the function is strict monotone. See, so now from this inequality, fx minus fy. So if it is strict monotone, it will be onto if and only if limit extending to infinity is infinity, or limit extending to infinity minus infinity is minus infinity, and it can interchange. Okay. Okay. So is greater than equal to log 1 plus mod x minus y. So we want to know that when x tends to infinity, where this function goes, right? So for this, put x equal to 0. Okay, so I think this is clear to you. So you can put, yeah, y equal to 0. Put y equal to 0. Okay, so this is clear to you. Log 1 plus mod x. I have skipped some steps, right? If you put, you will have f0, then you can use the inequality. I think it will be minus of f0 here, this side. Okay. Is it okay? Yeah, right. So now see, this implies limit mod x tends to infinity, mod fx is, you tell, anyone? That's easy to see. Please tell me. In this way, I know that you are engaged. It will be infinity, right? So that means, see, limit extending to infinity will of fx will be infinity or minus infinity. But if limit extending to infinity fx will be infinity, then limit extending to minus infinity fx will be minus infinity because of the strict monotone, right? Do you understand? It is not possible that this extending to infinity fx is equal to infinity, limit extending to minus infinity is, this is not possible, right? Because the function is strict monotone. Because the function is 1 also, otherwise it will not be 1. So it's a little exercise for you to think. Okay, so it means the range of f is so. Okay, by IVP that will take every value between minus infinity to infinity. So it will be a onto function. Okay, so any questions? And so I have told you another way to think that, so try to show that image is open as well as closed. Okay, that will imply that the image is whole of R. Okay, so let's move to the next one. So this one. Okay, so for this one, I will here give you an exercise. I will not prove it here because of the time constraint. So see, suppose that f and x equal to x to the power n into gx, where g is belongs to this ideal of C01 such that f0 equal to 0. Okay, so let's write it directly like this. Okay, continuous function, and g1 is 0. So in this case, this function will converge uniformly to 0. Okay, uniformly to 0, where g is a continuous function vanishing at 1. So you can prove using the continuity of g. Okay, so see, what this question says is that let fn be a sequence of functions defined on closed interval 0, 1 by fnx equal to x to the power n log 1 plus root x by 2. Okay, so here g is this function, right? Gx equal to log 1 plus root x by 2. So see that g of 1 is 0 here, right? That is, if you put 1 here, then you will get 1 log 1 is 0. Okay, so now can you tell me that which one of the followings are true? Can you decide and let me know? Let me give you 2 minutes. Okay, so raise your hand. Okay, so many of you have raised the hand. Okay, so who will tell me the correct answer? Let me name one someone. Abhinesh, बताइए. So let me know. So Okay. Nidhi, you tell.
Sir, first option and fourth option.
Okay, converse point-wise. That is okay. And this is okay. Right. So anyone have any questions? Because this
Sir,
sequence will converge uniformly. Yeah, please ask.
sir, can any alpha belonging to close 01 take place of 1? Like we take the maximal ideal G alpha is equal to 0, alpha belonging to close interval 01.
Yes,
Okay.
the procedure will be same like that. Okay, you can prove it. So I will not say yes, just see it. Because I have given the exercise. And what do you do when proving for one, and just see that one plays some role or not? Because for alpha, I think it's enough. Other than one, there is no need to any set x equal to alpha. Okay, that will be converge uniform, might converge uniformly. So do you know why? Okay, so do it. Okay, so I mean, there is no need to suppose that if you take this function at just in the interval 0 alpha, where alpha is less than 1, then do we really need g alpha equal to 0 or we don't need? Okay, check it. So now this one, this is complex analysis question. So I will discuss questions from complex analysis, abstract algebra, linear algebra, and real analysis and ODE. Okay, and all problems are very good. You will learn a lot of things. Okay, so please pay attention. So this one is a nice complex analysis problem. Okay, so we will do it now. We will do it after this. So what this says, let X be an uncountable subset of C and FC to C be an entire function. Assume that for every Z in X, assume there exists an integer. And let me tell you, sometimes student interpret this problem wrong and they get correct answers actually. Okay, so let me tell you how. Because sometimes you might think that for every jet, there is a uniform M. Okay, some N works for all jet. In this case, so here is an uncountable subset. Suppose that X equal to C, right? So yeah, that will be enough, I think. X is an uncountable set, then you might think that, okay, the some derivative is going to be 0 for all Z in some uncountable set. Derivative is a analytic function of analytic function, right? So, and if it vanishes on uncountable set and any uncountable set has a limit pointed in by identity theorem, it should vanish everywhere. So it's 0. So it's a yeah, this derivative is 0. It means that it should be a polynomial, right? So you will get the correct answer. But the problem is that the n should not be uniform. Okay, for each z, for every z, I mean, for each z, the n might be different. Okay, so sometimes it happens in exam, right? You interpret something wrong and you get correct answers, and you do not realize the mistake at that time. But when you next time sit in another exam and you find that with the same thinking process, with the same argument, you made some mistake and you are in loss. Okay, so that's what I'm pointing out. So let's do it. So what it says that for every z there is an integer n, right? So this n will be dependent on z. So consider these sets AI, where AI is the set of those x, those z in x for which ith derivative at z vanishes. Okay, so it's easy to see that the x is the union of AIs. Okay, yeah. Someone unmuted. So please mute yourself. And if you want to ask something, you can raise your hand. I will come to you. Okay. So, okay. So this is easy to observe, right? If we assume that for each I, let AI denote this set, then X is the union of these AI, right? Because each AI is in X. That's obvious. And suppose you pick Z from X, then because some derivative will vanish at that. So it will be in some of AI, some AI, right? So X is the union of this. C. Now, X is uncountable. X is uncountable. So not all these sets can be countable because the countable union of countable sets is countable. So there exists some I. So this uncountable. So this implies there exists I belongs to N such that AI is uncountable. Uncountable. That means countable. So this means Fij equal to 0 for uncountably many Z. Many Z, right? So since this is again an exercise for you, since each uncountable subset of C has a limit point in it. Limit point in it. So by identity theorem, Fij equal to 0. I mean, this is for all Z, right? For all Z in C. This means F is a polynomial. And there are some words about this problem. Okay, so F is a polynomial. F is a constant function is not true, right? F is a 0 is not true because these can be eliminated also. See, this question can also be solved very quickly in the exam. So that way, let me tell you that suppose that you want to eliminate some options. So pick Fz equal to Z, right? The first one and the second one are wrong. There exists a compact set K of C such that F inverse K is not compact. Okay. So for that, you need to know that it's a polynomial. Only 2 can be eliminated. Because third is true, you have to prove that. So once you know that F is a polynomial, once you know that 4 is correct, then 3 is correct. Right? So see, I think that you need not to solve this in the exam, right? Suppose that 3 is correct. Okay. So once you have eliminated 1 and 2, suppose that 3 is correct, then the fourth cannot be correct. Because polynomials are proper maps. The inverse image of compact set are always compact under continuous map. So 3 is correct, then 4 should not be correct. Yeah, okay. So it's not part B question, right? So, but it would be part B, then you can solve just without this, what I have done here. So now you have to know that this is a polynomial, but 4 is correct, then third is correct. Okay. So once you know that F is a polynomial, this is automatically true. Okay. So suppose that this question has only one correct answer, then that argument should work. Okay. So now this problem from complex analysis, let's take this one. Okay. Then we will solve problems from both. How this happens actually. Okay. So now this one, this problem from complex analysis. Okay. So give me a minute. fix it.
Sir,
Do you have some
sir, ये
question?
third option true sir, third option true होगा क्या?
No, ये false होगा क्योंकि proper polynomial map हमेशा compact होते हैं. Sorry, I thought that.
And sir, first question में सर आपने options गलत टिक किया क्या? वो 1-1 आया था ना first वाला?
Yes. So it might happen. Okay, ऐसा हो सकता है. So आप लोग देखें पर मैं सॉल्यूशन सही बता रहा हूँगा. So in the third I said that actually I thought it's asking about that for every compact subset K, F inverse K is compact. Okay, so but it is there exists a compact set K of C such that F inverse K is not compact. So since polynomials are proper, so it should be wrong. Okay, thank you.
Yes.
So this one, okay, so let's read it. What it says: for every n greater than equal to 1, consider the entire function p and z, k goes to 0 to n, zk over k factorial. Which one of the following statements are true? So the sequence of functions Pn converts uniformly to an entire function on compact subsets of C. So everyone knows this, that P and Z converts uniformly to e to the power z, right? So that is the entire function. So we know all this. So 2, 3, and 4. So once you know the solution of one option of this, then you know all the options. So can you try it? Let me give you 2 minutes and raise your hand if you are able to solve it. Okay. Raise your hand. Raise your hand. Every compact set has a limit point in it. No, I mean every sequence has a convergent subsequence, right? In a limit point, in a compact set. I don't think that is needed or not. So I will see that. Okay. So which one is correct, Sangeeta?
Sir, first, third, and fourth.
First, third, and fourth. Okay, let's see. So see, second is not true because suppose that it is true. Okay, suppose each Pn has a zero in the set. So this is a disk ball centered at 0 with radius 2023. Okay. Then Pn Zn, this sequence is constant sequence 0, right? But where this sequence should converge? See, Pn Z converts uniformly to e to the power Z. So where this should converge? 0. Why? Yeah, it converts 0 because it's a constant sequence, but because of the uniform convergence, where it should converge. So pick Znk converging to L inside what I said, that every compact, any sequence in compact set has a converging subsequence. Okay, so let us take its converging subsequence. So P and K, Z and K is a constant sequence, and limit k tends to infinity. Because of the uniform convergence, this should come out to be Z and K equal to e to the power limit and tending to k tending to infinity Z and K, that is L. So this shows that e to the power L is 0, right? For some L. So that is not true, because e has no 0. Okay, so contradiction. It means this cannot be true. So what you have learned is that the zeros of, suppose that there cannot exist a sequence of zeros, right? Where Z1 is a 0 of P1, Z2 is a 0 of P2, Z3 is a 0 of Pn, Zn is a 0 of Pn, inside a compact set in C, not only in this disk. Okay, so same argument will work. So what this says, that there exists a sequence Zn of complex numbers such that limit n tending to infinity mod Zn is equal to infinity. It means that this sequence Zn converts to infinity, and each Zn is a 0 of Pn. Okay, so how to do that? And this is, once you solve this one, then the third one can be easily solved, because pick a disk. So R1, so such that it contains some 0 of Pn, because each Pn is a polynomial. So it has n zeros with multiplicity inside in C. So choose R1 such that R1 means the disk. Okay, so let's say D1, disk D1. Okay, so say with radius R1, so that it contains some 0 of P1, Z1, 0 of P1. Okay, so this one. Then now we will choose another disk whose radius is greater than D1, and it contains the 0 of P2. Okay, but can this is possible or not? Just let me know. So it might be possible that D1 is when we have taken D1, then all the zeros of this are inside, the zeros of P2 are also inside this. So Z2 need not be here. So Z2 can be here also. So can you tell me? But there is a Pn, so we can take Z2 might be here also, right? We choose D2, but it not be possible that for all n, Z1, Z2, all n Zn's are here, right? It is not possible because I have proved already it. Is it okay? Right? Not all Zn's can be inside D1, right? Where Z1 is some 0 of P1 and Z2 is 0 of P2. So there is some n. So pick some n. I mean, say D10, 0 of D10 is here, Z10. In this way, so every time you draw disk and get some element, some zero of polynomial. So you have a sequence. This sequence Z1, Z2 converts to infinity. Yes or no? Why? Because this sequence is not bounded. It's unbounded, right? Why it cannot be bounded? So we can just say, no need to draw this. Just pick some zero of Z1, pick some zero of Z2, pick some zero of Z3. Okay. So this is a sequence. You know, pns are polynomials, and you have a sequence. And I claim that this converts to infinity. Why? Because this is unbounded. This cannot be bounded. If it is bounded, then it will. So, I mean, this is a better way to understand this. Okay. So forget about what I told you just ago. So pick Z1 a zero of P1, Z2 a zero of P2, and Zn is a zero of Pn. In this way, you get a sequence, and I claim that this will go to infinity. If this will not go to infinity, it will be bounded, right? Or it's some subsequence will be bounded, because you might say that it will not converge properly to zero, but right, it might something like, for example, 1, 0, 2, for example. Okay, so 3, 2, I mean, it has some bounded subsequence. So, but it properly does not converge to infinity. See, that cannot happen because of the same argument I given to you just ago, right? Because if all zeros of some sequence are inside this, then e to the power z will have some zero. We have just seen this, right? So it means that must goes to infinity, and p to the power n zn is 0. And this one is correct. No, sorry, this one is wrong. And first one is correct, and the third one is correct. And C, the Sn denote the set of all zeros of Pn, right? And alpha n, see, this is also a sequence of zeros, right? Where alpha n is some minimum of mod z, z belongs to S. I mean, this alpha n is something like this. Alpha n is also mod of Zn, where Zn is a zero of Pn, right? C, fourth option. Sn denote the set of all zeros of Pn, and alpha n is the mod of some zero of, right? Whose mod is minimum. Then alpha n tends to infinity, and it's very obvious because I have already proved that no matter what zero you pick, you always get mod z tends to infinity, right? So that is also true. Okay, so any questions?
Sir, I would like to point out one thing. In the third example, you have done like if there exists any such sequence such that Pn of Zn is 0, then that Zn should go to infinity. You have
Yes.
said this. But the question is, does there exist such sequence? You are saying if there exists such sequence,
Oh, there will
Zn.
exist. There will exist because each Pn has zeros in C, right? I had pointed out that.
Understood.
Exactly. So give me a minute, and if you have any other questions, then you might ask. So you may ask. Okay. Okay, so let's move to the next one. So a linear algebra problem, and after this, there are very, nice problems from algebra. Okay, so group theory problems. So you might not have solved it yet. Okay, so so let me show you that problem. So how many of you have solved it? So this problem. Do you know the correct solution, just not the formula, and you know how to get that formula? And because you might see the formula anywhere, right? So, but the way you get that, do you know about this one? The number of invertible matrices over Z modulo T square Z. Okay, so I will be letting you know this after this one. Okay, so let's solve first.
Can you scroll up to the previous question? I want to take screenshot.
Okay, wait. So you no need to take a screenshot. I will share the PDF. Okay, immediately after the class end. Okay. So let us discuss this one. So now you will solve this, okay? And let's go very quickly. Consider the quadratic form qxyz, x square, xy, y square, xz, yz, z square. Which one of the following statements is true? There exists a non-zero u in q cube such that qu is equal to 0. First of all, write this quadratic form in this form, x transpose ax, where a is, so you can do that, a is 1, 1, 1, and 1 by 2, 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 and 1 by 2, right? Is it correct? Is it okay? So it is a positive definite matrix or not? Just check the principal minors. So one is positive and this one is also positive. What is the determinant of this matrix? So let's do that very quickly. 1 minus 1 by 4 minus 1 by 2, 1 by 2 minus 1 by 4, and plus the last one, 1 by 2, 1 by 4 minus 1 by 2. Okay. So this one is 1 minus 1 by 4, and the last one 1 by 4, right? 1 by 8 overall, right? 1 by 8. So it's positive if my calculations are correct. Is it okay? The determinant of this matrix is positive. So all the principal minors are positive. It means it is a positive symmetric definite quadratic form. So it cannot vanish on any element of R cube. Okay, so these two are wrong. Any non-zero element, I mean. So read questions, options every time very carefully. Okay, so there exists, there every. So sometimes you miss some phrase and you get wrong answers. So you get the loss of 4.75. So see, there exists a non-zero u in C cube such that q equal to 0. So this is always possible because see why? Suppose that you pick this z square plus z, just put y equal to 1, x equal to 1. What do you get? X equal to 0. Okay. Oh, no, that should have a complex root, right? We want to have a complex root. So try to get an equation, something like that, by putting suitable values. Do you get that? See, z square and 1, we can put it, and y equal to 0 and 1. Yeah, we get this, right? X equal to 0 and z equal to nothing. Y equal to, y nothing, I'll tell you now. Tell you after this. So y equal to 1 or y equal to 0 maybe. So if x equal to 0 and y equal to 0, then we will not get that, right? Y equal to 1. So this will be 0, this will be 0, and this will be z square plus z plus 1, right? This quadratic form will be z square plus z square plus z plus 1. If you put x equal to 0, y equal to 1. Yes or no? React if you can see that. Yes, right? So why did I do that? Right? The question is that. So because if you see all these, then do not try to pick directly complex values, right? I square omega, that will take time. Because, once you fix x or y, it will be a polynomial in Z, and every polynomial has a root in C. So once you get an irreducible polynomial, that will have complex roots, and you are done. So that's what I try to do. I try to make it something like z square plus z plus 1. It's a reducible polynomial. So z will have values omega. So you have this non-zero vector in C, which will take 0 value in this. Okay. When you plug in this value here, you will get 0. An easy way to think, right? No need to pick many values. And because sometimes you may waste a lot of time, right? Picking values, but you do not get the correct one. You do not get it 0, and you might spend 2 minutes, 3 minutes. But if you think in this way, then you do it in just 1 minute. Okay. So, and this is correct because I have already done it. So the real symmetric 3 cross 3 matrix A which satisfies this for all is invertible, right? I have already checked that. So now let us solve this one first. After that algebraic problem, what I told you. So this one. Which of the following statements are true? The G1, let G1 and G2 be finite groups such that their orders, order G1 and order G2 are co-prime, then any homomorphism from G1 to G2 is trivial. That's very obvious. See, suppose F is a homomorphism from G1 to G2, right? Then image of G1 is a subgroup of G2, right? It divides, image of G1 divides. So image of F, I should say. Image of F should, order of image of F should divide order of G2. And this also should divide order of G1Y. Anyone of you? So, but any number which divides order of G1 and order of G2 must be 1, right? Because their orders are co-prime. So it means image of F has order 1. That means F is a trivial homomorphism. Now, Y image of order of image should divide the order of G1? Anyone? Quickly. Just quickly let me know.
Because G1 quotiented by card F is isomorphic to image of F.
Okay.
And
yeah, G. Okay, that's enough to say. So see, 2, let G be a finite group and F G be a group homomorphism such that F fixes more than of half of the element of G, then Fx equal to X for all X. See, it is very easy because as I say that the image of F, question number 2. So 2, option number 2. See, image of F contains more than half of the element, it means, right? If F is a homomorphism, then image of F according to 2 contains more than half of the element. Yes or no? Because if X, image of X is equal to X, it means more than the half of the elements of G are in the image of F. See, image of F is a subgroup. Its order is strictly greater than order of G by 2 and less than and equal to order of G. G2, sorry. G2, what do you think the image of F should be? Oh, so it says that it fixes, oh, sorry. I mean, it's onto, okay. I prove that it's onto. Okay, so it's onto, can you tell me that why it fixes all the element now? So I don't need to prove it onto, by the way, sorry. So I was thinking that it is asking about onto. So it says that F will be identity. Can you tell me why? And G is a finite group. Suppose that some element is not fixed. Okay. See, some element is not fixed. Y is not fixed. So Y has different image, right? Fy is not equal to Y. So F, suppose that the half of the element x1, x2, dot, 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 xn, these are half of the elements. So what will be the image of these elements? These are distinct element, right? These are distinct element. So image of these element will be x1y, y, the image of fy, x2, fy. So it means that these elements are not also being fixed. Can you see? This goes to this, this goes to this, this goes to this. X1, y is not equal to x1, fy, right? Because y is not equal to fy. So half of the elements are not also going to be fixed. But that cannot be possible, because only if F fixes more than half of the element, then less than half of the element can be non-fixed. Cannot be fixed, right? So that's a contradiction. Do you understand? So it means there is what is the problem? Why do we get contradiction? Because we assume that there is some element which is not fixed. It means all the elements are fixed. Okay, so this is the wrong assumption. Now, so this not needed. Okay. This is correct. This is correct. Let G be a group having exactly 3 subgroups, then G is a group of order p square for some prime p. So, see, first of all, G should have order p to the power k. This can be done here. It is very easy. P to the power k, right? Because if two elements, say p or q, 2 primes divides the order of G, then there are 4 subgroups at least. One is identity and one is element. I mean, suppose A is the element of order P, the group generated by A, and the group generated by B, where B is the element of order Q, and the group itself, right? So there is only one prime which divides order of G. Now, and order of G must be P square. Now it's easy, right? Because if its order is P cube, then by Silo theorem, you have subgroups of order 1, P, P square, P cube, etc. Right? So you have more than 3 subgroups. So order of G must be P square, and also it must be cyclic. So it's your work to prove. Okay. I'm not going to prove that. Any finite abelian group G has at least D order of G subgroups in G, where DM is the denotes the number of positive divisors of order M. So 4, 1, 4. So suppose order of G is M, then it has at least DM subgroups, the number of divisors equal to the number of divisors. So can you tell me why? Anyone? It's true, by the way. Raise your hand and let me know, because finite abelian group has a nice structure. It's product of cyclic groups. Okay. Okay, so Aman, you tell.
Finite abelian group, it has a product of cyclic group structure, and cyclic group has a property that if some positive number dividing the order of the group, there is just exactly one subgroup of that order. So from there we can do it from.
Sir, converse of Lagrange theorem can be also used, because we have been given finite abelian group, na?
Yes, the converse of
so
Lagrange
at least
is true for finite abelian group. So right. So now this one, this is very nice one. So let's do it. I'm sure that you will enjoy it. So let G be a group of 2 cross 2 invertible matrices with entries from Z modulo 9Z. Let A be the order of G. Which one of the following statements are true? The order of A is, you have to find the order of this. Okay. or following options. So students usually make a mistake. See, you have read about the order of this one. The order of this one is known to you, right? Z modulo PZ. I mean, here you can take N. Everyone knows its order, right? So, and how it comes, you also know that it is product P to the power N minus P to the power I, where I goes to 0 to N minus 1. So sometimes you can think that this is also true for this, but this is not. Okay, first of all, what does this mean? It means that those matrices from M to Z, 9Z, for which determinant A is. So how many of you know that? Raise your hand. Determinant A, equal, not equal, or something. Raise your hand if you know the definition. Just want to see that how many of you listening to me. Raise your hand if you know the answer. Determinant of A should be okay. Kubendran, you tell. Determinant of A should be
not equal to 0 element in is it over 9?
no. It should not be not equal to 0. Sipa, you tell. So what do you think? You tell. You think the answer was same? Answer is same as given by last one or different? Sayan, you tell.
Not equal to 0.
Not equal to 0. Okay, so just a simple example. So do you think this matrix is invertible over invertible? Yes or no? How many of you think that this matrix is invertible? No, it's not invertible actually. 3 does not, I mean, what is the inverse of this? You might say the inverse of this is this. But 3 is not an invertible element in Z modulo 9Z. So determinant has to be a unit. Okay, so the answer is determinant is a co-prime to 3, or you can say determinant is a unit. Okay, so determinant is a unit. So this is the definition of GL2 Z modulo 9Z. So otherwise you will not solve it correctly. Okay, so let's count its order. So let me count the order of GLN Z P square Z. Okay, so we can count the order of also. So let us do for GL2 Z square P square Z. Okay, so see, first of all, you know, there is a natural homomorphism from this to this, right? Which takes A to A mod P square to A mod P. This is a ring homomorphism, right? So it will induce a homomorphism from this to this. Okay, what is the map? A mod So I'm just writing A, B, C, D. Okay, that will go to A, B, C, D. Bar. So bar has different meaning. So let me write here mod P, okay? D mod. Okay, so this is a homomorphism. You can check all this. If you don't know how this comes, why this is a homomorphism, then there will have a problem. You will not understand the solution. Okay, so this is a homomorphism. So see, how can we count its order? Because we know its order, and if we know the order of kernel of, and this is a onto map. Onto map. Anyone? Can you tell me that why it is a onto map? So let me tell you. Suppose you pick a matrix A, just take its lift here, okay? Lift. Just lift it to here. I mean, if you pick some element like A, B, C, D, then pick the lift of A. Okay? Lift of A means lift it to Z modulo P square Z. Okay? So see that it's a determinant. Determinant of A is co-prime to P, right? Co-prime to P. So it will remain co-prime to P. So it is invertible. B is invertible in GL to Z square P square Z. Okay. So in this way, the image of B will be A. So it will be onto. Okay. For example, suppose that this element you have, okay, 1, 2, 1, 0, 5, for example, not 5. So just take 4 and 3. Assume that this is invertible, okay? So 12. So P is equal to say 13. Then just consider this element here. Okay, that will be invertible here also. And its image will be this. Okay. So the region I have already told you. Now, what will be the kernel? Kernel of this map. Kernel of phi. So assume the homomorphism is phi. Kernel of phi, those matrices A, B, C, D in GL2 Z modulo P square Z, for which A is congruent to 0 mod 1, sorry, 1 mod P. Okay. B is congruent to 0 mod P. And so on, right? D is congruent to 1 and C is congruent to 0. So see, A can take these values, B can take these values, right? B belongs to this set. 0, P, 2P, dot, 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 P minus 1 into P. That means that P square minus P. P square minus P. And sorry, B and C will be there, and A and B can be 0. Just add 1 to every element above. Okay. P plus 1, 2P plus 1, dot, dot, dot. P square, P plus 1. Right? A can be anything from this set. Any element congruent. So can you tell me the cardinality of kernel phi now? Cardinality of kernel phi is just here P to the P elements A can be any one of the P elements and B can be anything from the P elements. So total choices are P to the power 4. So order of kernel phi is P to the power 4. Hence, by fundamental theorem of homomorphism, you know that this will be isomorphic to quotient of it by kernel will be isomorphic to GL to PZ. So hence its order will be order of kernel phi into order of GL. So no, P to the power 4, right? Okay, order of GL to PZ. So I goes to 1 to n minus 1, P to the power n minus P to the power I. Okay, so now if P equal to 3 and is therefore order of GL Z modulo 9Z, order of this is 3 to the power 4 into 3 square minus, so sorry, यहाँ it will be
P की power n square होगा ना?
So P की power
n square
by P to the power 4. So GL2 and P square minus 1, P square minus P. Okay. So the answer will be 3 to the power 4, 3 square minus 1, 3 square minus 3. Now you can check that it's divisible by what or what not. Okay. So this will be, in general, order will be this.
Sir, how it will be P power 4, sir?
P to the power 4 because A can take P values, B can take P values, C can take P values, D can take P values. So order of kernel phi is P to the power 4. Okay.
सर फॉर्मूले में P की पावर n स्क्वायर होगा.
n क्या है? अभी तो हमने GL2 लिया है ना, n स्क्वायर क्यों होगा? क्या है n?
सर क्योंकि n 2 है तो 2 का स्क्वायर हो.
हाँ ठीक है.
तो सर वो जो
मैं 2 के लिए कर रहा था. Just doing it for 2, okay, everywhere. So now you can generalize it using Chinese remainder theorem and all. Okay, set P to the power L होगी तो क्या होगा? Okay.
सर
हाँ
सर ये जो फॉर्मूले में जो सेकंड लास्ट लाइन है इक्वल टू P की पावर n जो आपने लिखा है P की पावर n.
No, it's P to the power 4. That is 4, not n. So my 4 is this actually. Oh no, मुझे लगता है हाँ मैंने 1 n लिख दिया. I want to write P to the power 4. मेरा n तो है ना, 3 की पावर 4 भी तो ऐसे ही लिखा है ना मैंने. हाँ लिखता हूँ मैं ऐसे 4 को, आई थिंक कभी कभार तो 4 है. ठीक है. It's okay. So now this is all I think from December 2023. Or do we have some more problems? Let me see. No. So there is a OD problem. Yeah, I want to discuss this one also. So let's paste it here. This one. So how many of you know the answer of this one? Raise your hand and let me know. And the way to solve it. You should know these kind of questions are asked every year in the CSIR net. Okay, so let me tell you. So who will tell me the answer? Okay, Tarak, tell me what is correct answers. What are correct answers?
So first and third.
First and third. Okay. First and third. Very nice. Okay, so let me tell you. how to solve it using existence and uniqueness. First of all, what it says, consider the problem. Let J be the maximal interval of existence, K be the range of the solution of the above problem. Then which of the following statements are true? So this one is given cos y. C. This is y equal to 1 line. This is y equal to -1 line. Okay. Y equal to 1 line. So y takes value 0. Y is a continuous function. So it will cross from 0. My claim is that it will not cross 1. In fact, it will never take the value 0. Okay. It will never take the value 1 or -1. Why? The graph, I mean, may not look like that. Okay. So obviously it's monotonically increasing. So we don't know now it's monotonically increasing or not, because cos y can be positive or negative, but it will be, I think. So see. So assume that this is the solution of this because it's taking 0 value. And if it say takes value 1 at some point, say this one, okay, yt naught equal to 1. Now this problem, y dash minus y square cos y, yt naught equal to 1. This has, first of all, it has a constant solution 1, right? The function y equal to 1 is a solution of this. You can put 1 here, right? You get 0, and this side constant function, the differential coefficient of constant function is 0. And 1 is everywhere 1. So at t naught, it's 1 also. And this is, since this function is already satisfying this ODE and it is taking value 1 at t0 also. So it is also a solution of this. So it has two solutions. If we assume that y takes value 1 somewhere, but the existence and uniqueness will be violated. It means that y cannot take value 1. Similarly, it cannot take value -1. As it is a continuous function, so it cannot cross 1 and -1. So it means that the range of y is a subset of -1, 1. Now it is exactly -1 and 1. How do we prove that? I'll tell you. So see, first of all, yj should be r, because how do you find the maximal interval of existence? You find like this: h is minimum, you take a rectangle a or b by m. But when this b is free from the bound, I mean, sorry, m is free from b, right? So then you get the maximal interval of existence is equal to r. Okay, you might have done that already, so I will not do it here. So see, y, whenever you take a rectangle, because y is already bounded, you will have this m is equal to 1 minus y square. Then if bound of y is 1, so this will be less than equal to, this function is also bounded, right? Because y is bounded. So bound is free from b. Free from b. So you can pick b suitably, and so that solution exists in every interval of the form -a to a. And in this way, you get the maximal interval of existence is r. But to solve this question in the exam, you should have already solved, right, such kind of questions. And now you can easily prove that limit extending to infinity, y must be 1, okay, and -1, something like that. First, try to show that it's a monotonic increasing, and using monotone, using the theorem, mean value theorem. Okay, you can prove that. So, but if you can't, I'm letting you know that where you can see all this solution. And if you want to see the solutions of CSIR NET, NBHM, GATE, TFR exams, which I have told, you can check out this YouTube channel. So I'm writing here name, in mathematics, where you can access solution freely. Okay, there are playlists which are very well organized, and the questions has been put in the order, so you can check out the solutions of all the question. And besides this, solution question, you will also get a lot of information about these competitive exams time to time. Okay, so you can check it out. And also there is a free mock test made by me. Okay, so in the Ing Mathematics website, you can also appear for that if you want. Okay, and the mock test level is very good. So the question level of the questions is similar like the last exam. Okay, so please check it out. So this is the name of YouTube channel name is, yeah, this is the name of YouTube channel. Okay, so let us solve this one now. This one. Okay, so can you try it now? I'll give you 2 minutes and raise your hand. So hint is that a normal matrix is diagonalizable. Okay. A normal transformation is diagonalizable. Raise your hand. If you have solved it, raise your hand. And I will write few questions from the mock test here also, okay? Okay, so let me tell you the answer. Suppose T denotes the matrix of it, okay? See, V be a finite dimensional complex inner product space for a linear transformation T V to V. Let T star denote its adjoint, okay? So if T denotes the matrix of T, so the trace of TT star is 0, right? But what is the trace of TT star? The trace of TT star is this. I goes to 1 to 1 to N. Tij are the entries of T, right? You might have already done this. because these kind of questions are asked in CSIR net a very long ago, I think. So, but you might have seen this, right? So, it is 0. It means that every entry of T is 0, right? For each ij. For each I comma j, it means T is 0. And secondly, V is 0, so just multiply by V star, okay? Then you get this is equal to norm TB square. Norm TB square equal to 0. It means TB must be 0. Then second one is also true. Now the third and fourth are very easy to do if you solve like this. T is diagonalizable, right? So this is similar to a diagonal matrix, say D1, D2, dot, 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 Dn. But so the rank and nullities of diagonal matrix powers T to the power K. So let us say it's D to the power K. Rank of T to the power K will be rank of T for each K, right? Because you can see that whenever you get to the raise the power K to D, then the rank of DK will be same as rank of D, right? D and T are similar. So this also holds for T, and nullities are also same if ranks are same. If nullities are same, so see, range null space of T to the power K contains null of T, right? Null space of T. So, but if their dimensions are equal, then they must be equal, right? So, for diagonalizable operators, nullity. So, what 3 and 4 are asking, because T is equal to T star self-adjoint, so it's a normal, and normal are always or unitarily diagonalizable. Okay, so it is just this is asking that if V is in V such that V is in the null space of T2 to the power n, then it is in the null space of T, because the null space are of T and T to the power n are equal. So this is true, and this fourth one is similar. Okay, so all four are true. So let me write a question from my side. Okay, so let me impose a problem. So you try to solve this. Okay. Yeah, so in the mock test, I had given a very nice problem. So, I mean, I thought about it. So it was a question from probability, but also from group theory. Okay, suppose G is a finite group of order 2026 and non-abelian. Let A be a fixed element of order 103 in G. Okay, B is randomly picked from G. Then what is the probability that B will commute with A? So try to find it out. And if you have attempted the mock test and already know the answer, raise your hand. Okay. So, okay. Now, those who don't know, please try to solve it. I will let you know the answer. This is one of the nice problem. Okay. So let me give you 5 minutes, okay, to think on it. And it's not very difficult, okay? You all can do it. Just try to think. I'm sure that you will able to do it. Use Stellio theorems and normalizers and all, okay? All you need to do is try, give a try. So, by the way, I would like to ask that who have solved it in the exam. So, how did you find this problem? अच्छा लगा या अच्छा लगा ना? सही है problem. Easy and difficult will vary. So, what was the answer, by the way?
Sir, 1/2.
Okay, 1/2 is the right answer. Okay, so anyone want to change the answer? It might not be right. Okay, so let me tell you, okay? So why? There's probability that it will commute with B is its probability is 1/2. See why? So first of all, number of elements which commutes with A. That is the cardinality of NA. C. G is non-abelian. The cardinality of NA must be strictly less than order of G, right? Because G is abelian. And the cardinality must be greater than equal to 1013. Greater than equal to. Because all the powers of A, the cyclic group generated by A is inside NA. Right? The cyclic group generated by A is inside NA. So that will have order 1013. It means the order of NA is 1013. Non-abelian, where we use that G is non-abelian. G is non-abelian because here, right, that NA cannot be equal to G. No. So here we have not used that G is non-abelian because actually you need to know that G is isomorphic to DNA first.
Yes.
Because A might commute with all of the elements, right? Because A might be in the center. So, okay. So this will tell you that the order of NA is strictly less than order of G. Why it should be isomorphic to D 1013? Because there are only two groups of order 2B. Okay. The 2026 is equal to 2 into 1003. If it is non-abelian, then it's a dihedral. If it is abelian, then it's a cyclic group of order 2p. So it's a dihedral group. So dihedral group, the center of dihedral group, you know that there are how many elements in the order, either two, in the center, either 2 or 1, right? When n is, I mean, if you denote the dihedral group of order 2n by dn, when n is even, then there are 2 elements. When n is odd, there is only 1 element. So its center is trivial actually. So trivial means no non-identity elements can be there. Okay, although only 1 order and 2 order elements are in the center. If you have suppose d4 or dn, then if its cardinality is 2, then there is a I mean the card order of the second element is 2, right? So but its order is 1013. So that cannot be in the center. So it means n is, now the probability is easy, right? P of E, let us say, denote the event by E, is 1013 by total number of elements, that is 1 by 2. Okay. So this is the answer. Any questions? No questions? Okay. So let us pick the another one. This one. Okay. A topological question. So raise your hand. Try to solve it. Raise your hand. Okay. I would like to see how many of you can do it. Okay, Priya, what is your answer?
Sir, 1, 2, and 4.
Okay, 1, 2, and 4. Okay, we will see it. Raise your hand, dear all.
सर 2 नहीं होगा, 2 के लिए काउंटर मिल गया x स्क्वायर.
ओके, 2 नहीं होगा. ओके. Okay, see. what it says, let P R to R be a non-constant polynomial. Which of the following statements are true? The preimage of a compact set under P is compact. This is true. First of all, you need to observe that limit mod x tending to infinity, Px h infinity, right? Do you know this? Everyone knows. Okay. So see, suppose K is a compact set and P inverse K denotes its preimage, and it is closed because of the continuity of P. It's closed because P is continuous. So I just want to know that it is unbounded or bounded. So if this tells you that it must be bounded, right? Yes or no? So how? Let me tell you that suppose that it is unbounded. There is a sequence xn, x1, x2 dot 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 in P inverse K such that xn tends to infinity. Okay, that means that P of xn, which is in K, right? But limit xn tending to infinity, Pxn will be mod Pxn will be. So it will be infinity, right? Because limit x tending to infinity, mod Px is always infinity for polynomials. So which is a contradiction because K is a compact set. So Pxn cannot satisfy this contradiction. So it must be bounded. Okay, no unbounded sequence is inside it. So it must be bounded. It means P inverse K is compact. The preimage of a connected set under P is connected set. This is not true, right? Need not true, because if you pick this connected set 2 and 4 and P equal to x, Px equal to x square, then see that what is its preimage? P inverse of 2, 4, say 4 and 9. What is its preimage? 2 to 3 union minus 3 to minus 2, right? This is the preimage of this. Yes or no? Which is not connected. Not connected. Now every point x has an open neighborhood ux such that restriction of P to ux is a homeomorphism onto an open subset of open set in R. What does this mean? This means that if you pick any point, okay, there is a neighborhood ux of that such that P from ux to some open subset of R, whatever be its image, because it is open, so image will be onto an open set of R. Image must be open. Polynomials are open, man. Not open, right? Need not be open. So that is a hint. So what is the polynomial which is not an open map, by the way? Can you tell me? So we'll think a letter something. A polynomial which is not an open map. Very easy, right? Because in Px equal to x square, if you take minus 2 to 2, what is the image of this? No, non-constant polynomial, right? So image of this is 0 to 4, right? So it means x square can go
0 to 9.
0 to 9.
9.
0 to 9. So this can work. How? Pick the point 0. You pick any neighborhood, then it's a not 1, 1 on that neighborhood. So it cannot be a homeomorphism. Homeomorphism is a 1, 1, right? So P cannot be 1, 1 on any U0, any neighborhood of 0. So cannot be a homeomorphism. This is incorrect. So x square works for 2 and 3 both. The image of a bounded set under P's bounded set, that is EG, because it holds for every continuous map from R to R. That's not very difficult, right? Because every bounded set contained in a compact set, and the image of a compact set is compact. Okay. So the image of a bounded set will come out to be bounded. Okay, clear? Any questions?
Fourth option is wrong.
Yeah, do you have any question?
Fourth option is correct, sir. This is the wrong.
Sorry, I couldn't hear you.
The fourth option is correct one, but you picked the wrong.
Yeah, it's correct. Thank you. It's correct. The image of a bounded set under P is bounded. Okay. So the last question we will discuss now. Let me choose which one I'm going to discuss. There are 3 remaining or more than that. So something from OD complex. I have discussed 2 problems. Okay, so, let us take this one. So this is something which you should, for which you should work smartly in the exam. Suppose you read this problem. Okay, suppose you read this problem and see. Consider the initial value problem. This has been given x square y double dash minus 2x square y dash plus 4x minus 2 equal to into y equal to 0. Suppose phi x is a polynomial solution. It means it has a polynomial solution satisfying 1 equal to 1 and 0 equal to 0. So a polynomial which is satisfying 1 equal to 1, 0 equal to 0. Which of the following statements are? So x is a solution because phi x equal to x, that also satisfies that. No, x is not a solution. You can check it out here, okay, by putting it, because it becomes 0 and this becomes 2x cube, 4x. No, it's not a solution, right? So, but x square, and you can look out the options also. See, phi x equal to x, phi 3 equal to 3. So phi x equal to x can be, or phi 4 equal to 16, phi x equal to x square can be a solution. Okay, so you can check it out. Okay, it's a solution. Very easy to check. Okay, see, 2x square minus 2x cube, 4x cube plus 4x cube, and very easy to check, right? 2x square and it's 0. So x square is a solution now. This one is true and this one is true. And you are done. Okay. Right? Okay, so let's stop here. It's a good time to stop because we will also have a feedback session. So as always, you might have been attending the classes in maths experience form. So Vinod sir is not available today. So you can give your feedback for the today's session. Okay, raise your hand and give your feedbacks. Okay, whosoever want to give. So raise your hand. So anyone who wants to give the feedback can raise their hand. Okay, so Aman, yeah, please turn on your videos while speaking. Okay, you can say, go ahead. Can you hear me, Aman?
Yes.
Yeah.
Can you hear me, sir?
Yes. You can turn on your video. Okay. Yes.
Yes.
Yeah,
Yes, this session was very productive, and it reminded me a lot of techniques that some of them I remember, some of them logics, and
Some of them. Sorry, I couldn't hear you. Some of them.
sorry. Some of these problems, the logic behind some of these problems, I have already done, and I can remember it. I can already remember it, and some of them I forgot. It has been a great revision for me to recall all these techniques to solve a problem, particularly that one in the GL2 Z by P Z modulo P square Z. That I know that whole procedure, but the way you explained it, it became more clear, and I can now generalize it more easily, and that instead it can come in my mind. So and you have also told us the quickest way to strike a point from where we can solve it, not only by looking at the options, but also solving it yourself, and then look at the options, and that is very effective in part C problems, and that has been very useful. Thank you for this session.